Now, so that basically finishes our discussion of though there's lots to be said about those the inverse and implicit function theorems. For now, we'll just move on to other topics in involving derivatives in several variables. One thing is this one. What about higher derivatives? So that's what I'll talk about today. So as usual, you open set. Let's first start with a real valued function, f from u to r. So I would like to talk about higher derivatives of this function. Now, just like the linear transformation, just like the first derivative was interpreted as a linear transformation, there are ways of talking about the higher derivatives in abstract terms as multilinear functions and so on. But that's not so useful as the first derivative as a linear transformation. So instead, for higher derivatives, one generally switches back to partial derivatives. That turns out to be more useful, even though it doesn't capture the whole picture. So what we'll do is we'll take the partial derivative approach. Suppose DIF. Remember, this is the same as in classical notation. This is del f by del xi. Exist at all points of u. And for all I equals 1, 2 up to n. Actually, I don't need all I equal to 1 to n. Even if it's for 1 I, that's okay. Suppose this exists at all points of u. We define. Now I want to let me call, and also let me call this j. This index as j, not I. Now we define di djf equal to di of djf if the right hand side exists. This is just notation. Nothing is being. I'm just defining this notation. The only difference between left hand side and right hand side is I've not put brackets. That's all. So classically, one would write it as del squared f by del xi del xj. This is defined to be del by del xi of del f by del x. That's all. This is all that I'm saying, except in new notation. Right. Now, if all the second order partial derivatives for all ij and is continuous, we say that f is C2. So this is a very important condition, I mean, which occurs often in practice. We say that a function is of class C2 if all the second order partial derivatives exist and are continuous. Now notice that in order to make sense of all this, I don't need full differentiability of as a linear transformation in the sense that we have defined. We are just in the realm of partial derivatives. But of course, we know that since I'm assuming that partial derivatives exist, second order partial derivatives exist, this means that, remark, since di dj f exists for all ij, that means that the first order partial derivatives are continuous for sure, right? Oh, sorry. No, this is not true. Sorry. I take back this. This is not correct what I wrote. Yeah, this just let's leave it like this. I mean, we'll not have occasion to somehow this topic is kind of disjoint from what we have been talking about in the sense that we'll not have occasion to talk about the derivative as a linear transformation. We'll be entirely in the realm of partial derivatives. But let me just leave it as a question. The wrong statement that I wrote, but I can still raise a question. You can think about this. This is not a homework problem. This is just a question for you to think about. If f is C2, does it follow that f is differentiable? In the linear transformation sense. In other words, more specifically, are the partial derivatives, actually it is what partial derivatives first order partial derivatives of f continuous. I don't know why this has become, it's displaying it as a very small screen. Let's see. Why is that? Is the picture okay? Is it suddenly shrunk?
Yeah, it's shorter. It's short. It's like you've changed orientation of the device.
Let's see. So how would I change this back? So let me go back to Teams. Joined. Hmm. I don't know why it's how to make it full screen. On my tablet, it's okay, but the sharing part somehow is there's something got
So,
messed up.
sir, one thing you could try is
Ah,
on the global settings, as in if you just drag down from the top of your screen, you see this auto rotate thing. Turn it off, and
on my laptop screen or the tablet screen?
on the tablet, on the device you're using to read, first make sure it is in landscape mode, and then
Yeah, but well, it is in obviously it is in landscape mode because let me see. Go
in
to
that case, maybe let's stop sharing and then start sharing again.
yeah, I can do that, but let me just see once again.
It's
Yeah,
at the
okay.
bottom of the.
Let me just try this. I'll go to portrait mode and come back to landscape mode. No, it's still very small. I don't know why. Yeah, I think it's a tablet problem. So let me just okay. So let's
Alternative.
stop. Let me log out from this and again come back. Okay.
So you can just
Right,
stop
okay.
presenting. It's the button at the bottom.
Oh yeah. Stop presenting and then start again. Ah, yeah, it's okay. Yeah, okay, good. Yeah, thanks. So let's go back to that. So the first order, the C2 condition, does it imply the first order partial derivatives of f continuous? Actually, the answer is yes. I mean, it's what I said is not wrong, but you have to argue this. It's not immediately clear. See, what we know about the first order partial derivatives is that their partial derivatives exist and are continuous. So why does it imply that? So it boils down to this question. If I know a function has partial derivatives which are continuous, does it follow that the function itself is continuous? So what do you think the answer is?
Yes.
So yes, why? I mean, if a function has partial derivatives of all orders, we have seen through enough examples that it may not be continuous. But here I'm saying that the function has partial derivatives which are themselves continuous, then the function should be continuous. And why is that? Okay, you think about this. This is something we have done. You don't have to do any calculations or write down any equations. It's just a one-line answer. That's all. We have done this in a slightly different form. That's all. All right. So anyway, this we won't have occasion to talk about the derivative as a linear transformation. I just mentioned this. Now here is the main theorem which I want to prove. Theorem. If f is C2, then Dijf equal to Djif for all I and j. So in classical notation, del squared f by del xi del xj equal to del squared or all I and j and at all points. At all points. This is something which is not at all obvious if you look at it at first sight. Why should it be the case that if I differentiate with partially with respect to one variable and then take another derivative, why should I get the same function at the end? Someone has written, Tuhin has written, if you are using any board, I can't see. I hope all of you can see this screen being shared, right?
Yes.
Yes, sir.
Then I don't know what the issue is. So, right. So this is, even though this might be a familiar fact, especially, I mean, if you in physics and engineering, this is used very routinely. But just the fact that one uses it routinely doesn't make it an obvious thing, right? I mean, you need a, if you just look at it, it's not clear at first sight why this should be true. But so we'll give a proper proof of this. And what we'll do is proof for n equals 2. I think Rudin leaves it as an exercise for all higher n. So we'll assume the domain with the domain vector space, Euclidean space is R2. It doesn't, the proof changes only slightly if you assume it's Rn. For n equals 2, then, so here's a more precise statement. A more sort of general statement is the following. The proof is the same. Suppose D1F, you don't need C2 is the point. You don't need the full force of C2, the C2 condition. All you need is the first order partial derivatives exist on U actually, and also I need this one partial derivative D21. These three things exist on U. So this is one condition. The second condition is D21 F is continuous at AB. Then D12F exists at AB and D12F at AB is the same as D21F at AB. So the only difference between this more general statement and what I said earlier, earlier I just assumed F is C2. Here we are not assuming that the other partial derivative exists. That's part of the theorem. I'm just assuming D21 exists, then I'm claiming that D12 exists as well. And the two are equal. And moreover, this is a pointwise statement. Here I'm assuming that D21 is continuous only at AB. Then the statement is true at AB. But these are minor technical points actually. For all practical purposes, assume that f is C2. Most of the applications f will be C2. So I'll present the proof in a slightly different fashion from Rudin, because Rudin's, it's not clear why he's doing what he's doing. But if you work backwards, or rather if you start trying to prove it yourself in a straightforward way, it will become clearer why he's doing that, all these calculations. So let's try to do it in a very simple-minded way. So this is the thing we are interested in. This. I want to get hold of D12. I don't even know it exists, but I want to show it exists and is equal to the right-hand side. But what is D12 F at AB? This is by definition limit. See, I'm taking the differentiating with respect to the first variable, but the function being differentiated is this thing, D2F A plus H B minus D2F AB divided by H. So if the right-hand side exists, we say the left-hand side is makes sense. I mean, the notation comes into play only when the right-hand limit exists. So we want to establish that the right-hand limit exists, and in fact, we want given epsilon greater than 0, there exists delta greater than 0 such that this limit h going to 0 there's too much lag. This red screen is coming every now and then. So this limit minus, after all, we have a candidate for this limit. So we want to say that this limit exists and is equal to, remember that this is supposed to, we are looking at the left-hand side, that is supposed to equal D21 minus D21 F at AB. So this entire thing should be less than epsilon. And this should hold for all there's no longer this limit sign here. This should be less than epsilon for all h with mod h less than delta. So this is what one is aiming for. Now, now you go back and look at this again. You then just write down the definition of D2F. What is D2F? I.e. modulus of limit k going to 0. D2F is, in the first one, it is A plus H. H is fixed. B plus K minus F of A plus H B divided by K minus, in the second D2F, in this one, this thing here, it's at AB. So it is minus limit k going to 0, f of A B plus K minus f of AB, whole thing divided by K though these expressions, these two limits are the first order derivatives, and then minus d21f AB, absolute value of this whole thing divided by h. So I'll just put it as h inverse multiplied by this less than epsilon. That's what we want. Now I just combine these two terms, these two limits. It's the same k. And then I'll do that. And then also, I should be a bit careful. This is not, this H inverse does not come out of this. H inverse is only here, this part. This H inverse is not along with this one. So I'll write it as modulus of H inverse K inverse Q minus A less than epsilon, where this Q is just this, I just combine the numerators of these two expressions. So it is f of A plus H, B plus K, minus f of A plus H, B, minus f of A, B plus K, plus f of AB. There's a minus sign here, so all this I'll get this thing, and A is just the d21, the partial derivative at AB. So I want this. Now notice that I've removed the limit sign. Well, one way of making sense of that is, I mean, the only way of making sense of that is that for all HK with mod H less than delta, and K also I can put less than delta. So I leave it to you to figure out this one, that how I can remove the limit sign here. See, to say that this whole thing less than epsilon for mod H less than delta would amount to just saying that this quantity less than delta, but now all I've done is I use the same delta for K as well. So there should exist a delta such that if mod H less than delta and mod K less than delta, and if I have this inequality here, that is the same thing as saying that this thing should hold. So this thing and the next thing should be the same. That's the gist of it. So I'll leave it to you. Check that this statement here and the previous one are the same. It's a matter of just understanding what limit means. That's all. Right now, this Q notation that and Q and capital A is used by Rudin. So, oh, sorry, this is not Q. This is what he calls delta FQ. Delta F comma Q. Delta FQ is this one. Okay, so for simplicity, let's just assume it doesn't really matter. As for simplicity, assume H and K are positive. Then the picture is like this. So this is my open set U. I have AB. I've taken a small rectangle. This is A plus H B. This is A plus H B plus K. This is A B plus K. This rectangle is Q. This is the same as AB cross, A. This rectangle is, as a Cartesian product, it is just A plus H cross B plus K. So I've assumed that H and K are small enough so that I have a small rectangle. This is my point of interest, AB. I just taken HK greater than 0. It doesn't matter. If one of them is less than 0, you'll get a different rectangle with one of the vertices as AB. So you are evaluating F at the 4 vertices of the rectangle with various signs. Now, this geometrical interpretation is not really needed. It's one, but it helps to draw the picture to some extent. Okay, so the upshot is that we are in the process of proving that this delta F comma Q divided by HK minus A less than epsilon if mod H less than delta, mod K less than delta. If we prove this, we are done. So, so let's do that. Then let's just prove it then. So now I'm going to define, basically it's mean value theorem applied a few times, 2 times. Let's look at f of ut equals f of t comma b plus k minus f of t. So in this, that's why that rectangle picture is slightly useful. So what is this ut? Oh, here I need b. So I'm just looking at f restricted to this line, that's all. So this is the value t. The x coordinate is t. The y coordinate is varying between b and b plus k. So I get this vertical line here. Oh, I don't know why there's so much lag. Okay, so I get this, and then the point about this function u. Oh, it's still not. It's not. The function u is that this delta fq can be written as u of a plus h minus u of a. Then I have this. Now, once you write it like this, of course, immediately the first thing which comes to mind is the mean value theorem will tell you that this is the same as h times u prime x for some x in a to a plus h. By the way, in order to apply the mean value theorem, obviously you have to observe that u is differentiable because why is u differentiable? Well, u is essentially a function of one variable. So the differentiability of u amounts to saying that it's a difference of two functions of one variable. This is a function of one variable, this is a function of one variable. And these two functions are differentiable because I have assumed that d1f exists at all points. Because of this assumption, both of these are differentiable. The difference is one minus another is differentiable. Therefore, I can apply the mean value theorem to u. So I get this all right. So, well, this is the h times. Now, in fact, whatever I said here, these two are differentiable. Not only are they differentiable, their derivatives are by definition d1f and d1f evaluated at different points. So the first derivative is d1f at x b plus k. The second one is d1f at x b. Right. So now, since since d2f exists everywhere, I can apply the mean value theorem to again now to this expression here. I regard it as a function of we can apply mean value theorem to the function let's say s going to d2f at x s. Previously, I had considered on this vertical line segments. Now I am basically regarding the function, not the original function, but rather d1f along this horizontal segment. So here no, I'm still in the vertical segment. It's just at a different point. Instead of t, I'm at x. What am I saying? No, x is fixed, so this is changing. The y coordinate is changing. So yeah, that's correct. So to the function, this function, mean value theorem to this function to get, well, oh, not why did I write d2? It was d1 here. d1 to get y in between b and b plus k satisfying that this difference, basically this difference is equal to d2 d1 f at x comma y multiplied by k. This should be equal to what was it? D1f at xb plus k minus D1f at xb. Okay, so I've applied the mean value theorem to the first partial derivative and I get this. So if I plug it in back here, there was already an h here. Now I'll also get a k. So the upshot is that delta fq is equal to h times k and then d2 d1f at xy. Well, why did we even start looking at this? Because we had started with this expression. We wanted to show this delta fq divided by hk minus a. What we end up with, so we have found that delta fq is hk times something. Therefore, what we want is the hk cancels off. If I plug it back, this expression in the original one, we want d2 d1f at xy minus a less than epsilon. And remember that a was by definition d2 d1f at ab. Now this almost gives whatever we want, because after all, what are we saying? We are saying that, by the way, that in the original thing, whatever we wanted, remember that we had this h and k. This thing, this inequality was supposed to hold if mod h and mod k are less than delta. Now, in the way we have, in the final expression that we have, this h and k have disappeared. So how does, I mean, how do we use, how do we, so this should hold if mod h, mod k less than delta. So where should this play a role? Well,
Sir, are we given that D21 is continuous?
yes, that is true. But where does, I mean, it's in terms of xy, where does this role, where do this h and k play a role?
We know that X has to lie between A and A plus H.
That's the point. So the point is just that x, which was obtained from mean value theorem, x has to lie between a and a plus h, and y has to lie between b and b plus k. That's all. So if h and k are small, x will be very close to a. It lies between a and a plus h. Similarly, y will be very close to b. So you're done. Therefore, the continuity of d2 d1 f at AB gives star. Let's call this star. That's it. If h and k are small enough, x and y will be sufficiently close to AB, and the continuity will then guarantee that this will hold. So this proves that. So the proof is not very mysterious. It's something very natural. If you just start with what you want, that's the main thing. So you just write down in a very simple-minded way, you write down the difference quotient. I mean, after all, what do you want? You want to show that D12 F at AB is D21 f at AB. You know the right hand side exists. You don't know that the left hand side exists. Even if you knew, it doesn't help all that much. So you just start with the difference quotient, which will define the left hand side like this, what I have here. Then you just simplify things. So you'll get 2h and k. Two things which are going to 0. Then you define, just for convenience, you define, put it like this notation. The heart of the matter is estimating this quantity here. Using the mean value theorem twice to basically see what this quantity is. There are 4 terms here. Use mean value theorem 2 times and simplify. That's it. Okay, so but this fact that if f is C2, then the mixed partial derivatives, second order partial derivatives, it doesn't matter which order you take them in. It's very important, and it's sort of used very routinely everywhere. But as I said, it's not an obvious fact if one stares at it. Now, here's an application which you will see. This is an application which is very helpful in complex analysis. In your next semester, perhaps you will take a course in complex analysis. It's used there. It's used in many different places, but certainly in complex analysis. So let's look at this setting. On first sight, it will seem like something a totally different question, but we can reduce it to that mixed partial derivative question. So let's look at a function of 2 variables. So this is from a rectangle. So this is AC, then BC, AD, BD. Let's look at this function of 2 variables, and then I want to ask, I'll integrate with respect to the first variable. The exact conditions on this I'll define in a second, but let's put it in a simple-minded way. So see, what I'm doing is I'm integrating with respect to the first variable. So x is changing. So along these horizontal lines, then it becomes a function of t. For each line, for each t, I'll get a number by integrating this one. Then I differentiate that function of t. Is it the same thing as, so first integrating, then differentiating, is it the same thing as first differentiating and then integrating? So it's a question mark. Obviously, in order to make sense of this question, I said that f is a function. That's In that generality, the question doesn't even make sense. For one thing, you need some assumptions on phi, obviously, that for example, for every t, this phi of x comma t should be Riemann integrable here. That is one thing. Second thing is, for this expression to make sense, I need to know that phi has partial derivative with respect to the t variable, and that's also Riemann integrable. And also I need to know that whatever I get in the brackets is a differentiable function of t. So you need some conditions for this to make sense. But even if assuming everything was nice, say for example, phi is C1, let us say, then it's not clear why this should be true. That why should the first taking derivative and then integrating should give the same answer as the other way around. The thing is, it is true under some very minimal conditions on phi, lesser than C1. In fact, you don't even need C1. You need something slightly different actually. Assume that the function x going to phi of xt is Riemann integral. This is the minimum needed to make sense. Riemann integrable for all t in CD. Say for this, that at least makes for every t, this thing within the brackets makes sense. That's what this condition says. Now, the other condition is that, so this is one condition. The other one is D2 phi exists at all points and is continuous. So the way Rudin states it, it might be a bit confusing if you look at Rudin. The condition he gives looks a bit strange. It's I'll just state it and ask you how it's different from what I've written. Then d by dt this holds. By the way, this holds for all. Now, this derivative, this holds everywhere. What does everywhere mean? Well, when I say this derivative has to be evaluated at some value of t, right? And some value of x. So let's say at all x naught, t naught. Whatever I get here, this thing also evaluated at x naught, t naught. Now let me state Rudin's condition. Instead of this condition, Rudin puts it like this. And let me ask you how this Rudin's condition is more general. Instead of 2, it is enough to assume the following. Given S, in between A and B, and epsilon greater than 0, there exists delta greater than 0 such that d2 phi at xt minus d2 phi at xs less than epsilon if t minus s less than delta. Okay, so now my question is, look at this expression here, whatever we have here. How is this different from saying that d2 phi is continuous? So this is one condition, and this entire thing is another condition. So I claim that this bigger box is actually a weaker condition than the smaller box. So why is this weaker?
Because it does not demand d2 of x comma s to be defined.
d2 of phi, well, d2 of phi is defined at all points, that's for sure. I mean, even for this bigger box, d2 of phi is defined at all points, otherwise these expressions don't make sense. There is one obvious way that this is weaker than this, but there's one more subtle way also in which this is weaker. Okay, so tell me, what is the obvious way that this condition is weaker than saying that d2 phi is continuous? It's just a matter of the definition of continuity. Look at what we are, the points at which this things are being evaluated in this expression here. It is x comma t and x comma s, right? Now, when I work with full continuity, what will the similar expression look like?
Oh, we have restricted our domain to simply just y instead of varying x as well.
That's correct. So when I work with full continuity of a function, I don't fix the same, take the same x for both. I mean, it's continuity of a function in R2, not continuity of function in R. So I'll have to vary x as well. As long as I have x prime t and here xs, all I require is x prime is close to x, t is close to s. Then I would say it's continuous. So I should be free to vary this one as well and still demand difference is small. Here I fixed, I'm restricting myself to lines, vertical lines. In the rectangle, I'm just looking at continuity along the vertical lines. That is one thing. But I can't even replace. So instead of putting it in this funny way, explicitly spelling out the definition of continuity, why didn't I just say, why doesn't Rudin say that d2 phi restricted to vertical lines is continuous? This is the more subtle point. This condition is slightly stronger than just saying that it's continuous restricted to vertical lines. This has to do with the order in which things appear here. There are lots of things, right? S is there, epsilon is there, delta is there. And then, of course, T is just constrained by delta and S. T is not really there. What is the three things are S, epsilon, and delta. So
The
yeah,
the same delta has to work at all x.
exactly. That's the point. The same delta, see, given S, where is S? Yeah, given S, this should hold. Oh, by the way, here I should have said this if S and for all X. So this should hold for all X. So the same delta should work as long as the S is somewhere here. As long as this S variable is fixed, the same delta should work along all the lines for all the lines, vertical lines. So it's a weird condition. Now, by the way, that issue will arise. Suppose I assume D2 phi is continuous. How can, yeah, that raises the question. If I know that D2 phi is continuous, so you're absolutely right that the same delta should work for all the vertical line segments, all X in other words. But if I know D2 phi is continuous, how do I know that this condition is satisfied? I mean, again, the same delta should work and so on. That issue will arise, right? After all, continuity is at a point. So how do I solve that issue? There is a theorem involved here. Continuity at
the compact set.
what does it say? If its function is continuous, uniformly continuous. So that is a fact which is being used here. So if I know that D2 phi is continuous on this compact set, closed rectangle, then I know that it is uniformly continuous. Once I have uniform continuity, of course, I have something much stronger than what I have here. It will work on every any. I mean, I can even change the X variable also. So the same delta will work not only along vertical lines, but I can even if I'm free to change this, it will be fine. So this will imply this by uniform continuity. So these things are sort of assumed. Rudin doesn't even state it explicitly, but it is there that uniform continuity is the crucial thing. Now I'll have to stop here since I'm out of time. So the proof of this, anyway, the proof is not that difficult, but again, it's a matter of, as I said, there is no C2 function involved here. You might wonder where second order partial derivatives even come into play, because here we are just talking about first order derivatives and integrals. Obviously, well, yeah, and in fact, why do we even need this condition on second order derivative of, no, not second order derivative. This is just the first order derivative, that's it. But how do we use that theorem? Here is the question. So anyway, let me just 1 second before I end today's lecture. Let me just make one remark and then stop. We drop this and then theorem 7.16. Oh, actually, yeah, I will make a correction. This is not quite an application of that fact. This is a separate fact. So this, you don't need that second order thing here. Mixed partial derivatives. So it's not quite an application. So this is just a separate topic. Interchanging derivatives and integrals. But again, the point is, again, the proof is again involves mean value theorem, as you can expect. Mean value theorem for one variables. So I'll just present the proof in a recorded lecture and post it. So, okay, we'll end today's lecture. We'll again resume on Wednesday. Now, in Rudin's presentation, somehow he presents determinants before all this, which is which doesn't make sense. I mean, why he presents it before this is not clear. Determinants are going to play a crucial role in the next major topic we are going to discuss, integration of multivariable functions. So I'll deal with determinants when I come to that. So I'll discuss this and give an application of this theorem here, interchanging derivatives and this thing. As I said, it's going to be applied in complex analysis, but there's another nice application in Rudin. I'll discuss that and post it as a lecture. So we'll stop here. Any questions? So shall we end today's lecture? Can you hear me?
Yes, sir.
Yes, sir.
Okay, fine. Yeah, okay then. Yeah, bye.
Okay, thank you, sir.
Yeah, bye.
Thank you.